So it looks like uh, the integral between 0 and pi divided by 4 of sine to the 3 divided by cosine this d theta. This is sine theta 1 minus cosine squared divided by cosine squared in d theta, and this is equal to um, minus integral in d theta and then plus integral this pi divided by 4 sine theta divided by cosine squared. So we get minus pi divided by 4 and then I guess minus 1 divided by cosine theta between pi 2 and 0. So this is minus pi divided by 4 minus square root of 2 plus 1. So it looks like, so the volume, so this guy, so star seems to be equal to 1/3 minus 1/3 times 1 minus square root of 2 minus pi divided by 4, which is equal to square root of 2 divided by 3 plus pi divided by 12. I don't know if this is even correct. Are there solutions of these problems at the end of the book? Let's see. No, there is something wrong. This is number 33. Ah, no, this is number 25. Ah, okay, well, I set a equal to 1 in the beginning, so this there is no pi. Yeah, I just set a equal to 1. It's not, I didn't want to overcomplicate the computations. Number 23 or number? Okay, so this gives me, it says that it's 16 times something. I understand the 16, but I get a different number. Why? There is a square root of 2. I guess I have done something wrong in the computations. Let me go back. Okay, so let's see. This looks correct. Yeah, this is the tangent. 1 plus, yeah. And then I have this sine to the power of 3 with a minus. Tangent to 0 is 0. Where did I get the 1/3 again? If I differentiate this, I get this 1/2, and then I have a 2, and then I have a minus, and then I have cosine squared, and this is correct. And I have r. cosine square. This is a sine. So the integral of this. Hmm. There is a minus there. 1 divided by square root of 2 divided by 2. It is a square root of 2. I don't know, I get something different. I don't see a mistake. Maybe I just got the endpoints wrong. I don't know, it might be. I'm not sure, honestly. Let me see, double check one thing. Ah, no, there is a mistake here. Wait. Ah, yeah. Yeah, I'm stupid. I'm a stupid fucker. No, but wait. Yeah, this is wrong. I'm fucking this is sine of theta times 1 divided by cos this minus 1. I forgot to multiply. And this explains. I have to erase this. Okay, so then this is sine of theta divided by cosine squared theta d theta minus sine of theta in d theta. Now this is should be minus cos 1 divided by cosine 0, and this is plus cosine theta, doing this and the 0. Let's see. I get square root of 2 divided by 2 minus 1 from the second. From the second, and I get 1 minus square root of 2 from the first. And this is minus square root of 2 divided by 2. So star is equal to 1 divided by 3 minus square root of 2 divided by 2. Now this should be correct. Just one. Well, I don't know. I'm not sure about this 130 here. It might be something because here there is one and not one third. Where the hell is this one third coming from? Why is this problem so? Yeah, so this is 16. I don't know. There is a problem here. This one, I don't understand where this. Well, it should be one and not one third. But I'm not gonna waste more time. You'll find a mistake. Or I find a mistake after when I close the meeting and then the seminar, and then I'll upload the notes. Let's go ahead and do something.
Sorry, Daniele.
Yes.
Very quick, silly question about the previous exercise. Can I ask a question?
Yes.
The integral of a sinus of a cosinus square. How did it became 1 over cosine theta? Yeah.
Wait, what happens? What happens if you differentiate cosine theta? 1 divided by cosine theta.
Okay. Yeah.
Yeah, that's a primitive. You can do a change of variables again, but I mean.
Yeah. I see. So I thought, okay, you have the derivative and the numerator. Okay, thank you.
Exactly. Okay. This factor of 3, I don't understand where is this coming from. This. There is something wrong with the signs. Let me check one more time. I think I got some sign. Wait. Oh, there was a minus in front. Okay, so I get sine theta divided by cosine squared with a minus in front. So in the end, this gives me a plus. Well, a minus because, yes, so it's. I don't understand. This minus that I have in front comes from the derivative. When I differentiate this guy, I should get 3 divided by 2 times cosine squared times, sorry, minus cosine squared times 2r. And this is exactly what I get. And this is between 1 and 0. So I get 1 and 0. 1 minus cosine squared, which is blah blah, minus 1. And this is a plus. this plus is giving me tangent, and the minus I have minus minus 1 minus, so it's plus cosine, and then there is a minus there, and then it should be okay. So one more time. Star is equal to 1/3, and then I have minus 1/3 times integral cosine squared theta and d theta. So now we computed this goddamn integral here, and this turns out to be minus 1/3 integral between 0 sine 0 this sine theta. Okay, so this is what? This is cosine theta. But there isn't. I don't understand. I don't know if there is a mistake in what they do, or there is a mistake in what I do. I don't get it, honestly. Minus sign, yes, which becomes a I don't know. I don't see the mistake. For me, this is 1 divided by cosine theta, and then you do this. And what you get is what I got before. So I don't know. There is something. Either I do something wrong, or there is a mistake in the calculations. Yeah, but no, I do have a 1/3. It's not this the problem. There is a problem with the signs here in this parenthesis here, I think. But I don't want to waste more time. I mean, maybe there is a mistake in the book too. I don't know. Maybe I'm doing something wrong. Anyway, I'll check it later, and we can try to move ahead to something else. Okay, so let me give a look to the number 33 here. So what is this number 33 about? That's again another double integral. Why is this important and why I want to do that? Because where is the text of this problem? Okay, so we want to find the area of the region in the first quadrant. In the first quadrant, bounded by curves, by the curves xy equal to 1, xy equal to 4, x equal to y, and x equal to y divided by 2. So we have this. So what do we have here? We have two hyperbolas, something like this, and something like this. And then we have two straight lines, like this. So the region bounded is this red part. and we want to compute the area of this guy. So if I call this domain here D, we want to compute I, which is the double integral over D in dA. Now the question is here, I mean, if we want to solve this as a double integral, what I want to show you is that, of course, you can do other type of change of variables, right? So in this specific case, I want to do a change of variables, which is not the polar coordinates, but it's something else. So I introduce the change of variables uh, that is maybe u equal to xy and v, which is equal to y divided by x, right? Because I mean you can rewrite this bounds here in a smarter way. This is parenthesis. So I introduce this change of variables, and um, we need to compute the Jacobian of our transformation. So you can do, well, now I would need to compute the inverse of this transformation. So we do have u is equal to this, v is equal to this. Now this implies that y is equal to u divided by x. And if you use this, you get that v is equal to u divided by x squared, which implies that x squared, okay, but there is a square root that I don't like. Okay, let me just not compute the inverse transformation. I will just use the inverse formula for the Jacobian here. So let's see what's the Jacobian of this transformation. The Jacobian of this transformation, I take the derivatives with respect to this, and then we get that this is equal to y, and then I have x, and then I differentiate with respect to x, I get minus y divided by x squared, and then I have 1 divided by x, and this is y divided by x plus y divided by x. So it's 2 times y divided by x, which is equal to 2v. Yes, but we are interested in we actually need this, but you have seen in the class that this is equal to literally the inverse of the transformation. So this is going to be equal to what was v or u? V. Okay, so we have the Jacobian of the change of variables. So the integral that we had was I, and the domain, now written in these new coordinates, you see that this object is now, v is transformed is like a square, right? Because we are between 1 and 4 and 1 and 2. So we get that in the new variables, we have 1, 2, and 1, 4. Now, what I called what? U is between 1 and 4. So du, dv. And this is now the Jacobian. I don't put a modulus because v is between 1 and 2, so it's positive, but otherwise we would have needed the modulus. So we get 3 from the integration in u, and then we have this, 2 here, v dv. So this is now 3 times divided by 2 logarithm of v between 2 and 1, and this is equal to 3 times divided by 2 logarithm of 2. So this should be the solution of this problem. So you see that change of variables, it might be useful also for I mean, you don't need, I mean, it's not just polar coordinates. You have other type of change of variables that might be useful. So be aware of this fact. I want to conclude. We have 5 minutes. I want to conclude this seminar with the number 35. Maybe only one of the two. There are two different calculations to be done. So we want to compute this, y divided by x, and y divided this, dx dy. This is called I. And then the domain of integration is a triangle. Is this triangle here, which is red. This is T. So the point number A asks you to compute the integral I using the polar coordinates. That's going to be quite tricky. I leave this for you because I mean the change of variables is not the correct transformation to solve this integral, but still you manage to solve it anyway. So the correct transformation here to change the variables is the one which is suggested in the point B. So it is suggested to change the change of variables u equals to y minus x and v equals to y plus x. It's a linear change of variables, and you get that du dv dx dy very hard du dv dx dy. This is equal to minus 1 1 1 1. So this is equal to minus 2. So our thing will be 1/2, right? And we have to find out the bounds of our region. So new bounds for T. So it looks like V is going to be less or equal than 1 and greater or equal than 0, and U is less or equal than V and greater or equal than minus V. This is the new region. Yes, so if you see that if you do properly, you see that the region is transformed in something like something like this. It should be, this is V and this is U. This is the new triangle, maybe orange. And this was XY. So we have the new bounds for our region, for our integral. So what do we get? We get that I is going to be equal to 1/2, that comes from the Jacobian, integral between 0 and 1, integral between minus V and V of e to the power of u divided by V du dv. And this is equal to, we integrate in u first, we get 1/2 times this v between v and minus v in dv. This is equal to 1/2 we have v times e minus e to the minus 1 in dv, and this is going to be equal to 1 divided by 4 times e minus e to the minus 1. And that is all. So this is the result. And the point number A is left for you. Yeah, I have no more time left for you. Try to solve this integral using polar coordinates. Okay, so we are done for today. I will check this exercise I got stuck on and see if it is the book wrong or if it is me wrong, and I will upgrade or change, modify the slides, the notes, and then upload the correct version hopefully by today. So if you have no questions, feel free to go.
Daniele,
Sure.
how would you write the in the domain for the R in part A? Would you use the sign this time?
Yeah, you have to do the same trick that I was doing in the previous exercise. So you have this triangle here, like this, right? So now you have that. So specifically, this triangle, I think it is. I mean, this angle is pi divided by 4, and I think this angle is pi divided by 4 too. So now here you have a radius. This is the radius r, but this radius r depends on theta, right? So you have that's I'll do a bigger picture. So the triangle is something like this. So this angle is pi divided by 4. This angle is pi divided by 4. Then you have some radius. This is r, and this is theta. Now theta will be between 0 and 2 pi. No, from 0 and pi divided by 2. Now you have r, and you have to find out what is r as a function of theta. And now here you have to use theorems on triangles again. This angle will be pi minus pi divided by 4 minus theta, which is 3/4 pi minus theta. And then you get that by theorems on triangle, the ratio between okay, let me use colors. The ratio between this side and this angle, or sorry, the sine of that angle is equal to, let me use orange, and this angle here. Or maybe orange was an unhappy choice. Let me use green, and this. So this theorem on triangles tells you that the red, which has length 1, divided by the sine of the angle which is opposite to it, which is 3/4 pi minus theta, is equal to r, length of the green, divided by the sine of pi divided by 4. So once you have this expression, you can solve for, you get that r is equal to the square root of 2 divided by 2 times 1 divided by sine of 3/4 pi, minus theta. Now you can use the summation formula, or whatever it is called, and you get something like, I mean, this disappears actually, this constant. You simply get 1 divided by sine theta plus cosine theta. So this is your function r. I mean, your r as a function of theta. and then you have to use that as an endpoint. So R will be between 0 and that thing that I've written here.
Sorry, Daniele, there is a question in chat about, I think, the last and the penultima, how you get the boundaries. I'm also curious. I have the same question.
Which one?
The last, yeah, this one, and for me, even the previous one. The boundary here, t equal v between 0 and 1.
Well, in the previous one, it's clear. I mean, you're in this slide that I'm showing. You're between straight lines and parabolas. So the parabola, I mean, xy is equal to, you're between xy equal to 1, xy equal to 4. So when you
Yes.
change the variables, this becomes a new variable. So, and the same thing happens for the straight line. You just divide by x both cases.
Yeah. I see. U became 1 and U became 4. Yeah, absolutely. Very clear.
Yes.
Sorry.
So this becomes a rectangle.
Yes, because this is the Jacobian, and you can, yeah, helps to.
Yes, in the next case, what were the original?
The original.
Okay, so we had let's see what did I do? Yeah, because yeah, I see. Let's see, what did I do? What did I do here? But let me just write one thing here. It's actually not a rotation. Well, I mean, I guess that one way to do that would be to I mean, the transformation that I am applying is linear, is A, is this one. So I just take the straight line x equal to 0, y equal to 0, and the third one, and I just apply the transformation to those straight lines, and I see what I get out. It should be a rigid transformation, this one. Well, not really. What happens if I apply this transformation to x equal to y? So this is going to give me I mean, let's see if this is convincing. So this is now the number A, and I'll leave it here left for you. So the change of variables, the linear transformation that we had was minus 1, 1, and 1, 1. So we had a triangle like this. This triangle is essentially made by three straight lines. One is so A times the vector t0 gives me minus t, which is now the straight line y equal to minus x, how it is supposed to be. And this is giving me tt, that gives me x equal to y. So I mean, the straight lines, you see, I mean, they are sent in this straight line and in this straight line, and then I have the third straight line or a segment thereof, which was y equal to x minus 1, I guess, or x plus 1. No, minus, sorry, minus x plus 1. And again, when you do t s minus t plus 1, what you get here? You get minus t wait a second, should get something vertical. Is this even correct? Yes. Minus t plus 1, t minus t. Ah, yes, sure, of course. T and this is plus 1, so you get minus 2t plus 1 is minus here, and this is 1. So now you see that this is now constant in the y direction, so it must be this straight line here. And now you get the, I mean, now it's clear, right? I mean, yeah. This is a linear transformation. I'm sending the basis E1, E2 into another basis, and then it's essentially a rotation, even though the determinant is not 1, it's minus 2. So is it more clear now? How do did I get it? Yeah. I mean, this is one way to see. Of course, not all the transformations are linear. I guess that otherwise you have to play a little bit with the expressions and then see what happens. Because yeah, in the previous case we did have what did we have? X between 0 and 1, and y between x and no, x between y between 1 minus x and 0. This is the triangle. Now if you sum x to this inequality, you get x less or equal than y plus x less or equal than 1. So this is actually one of the two variables that was u. So the first upper bound you get no, wait a second, was it u? Yes, it was u. But then I have x there. Let's see if it is possible to see that better from the geometry here. Because this is not. if I instead, if I reverse this, what do I get? Minus 1 less or equal than minus x, so equal than 0. And then I add both sides y. I don't know, I'm just trying. So I get this. Now this was b. But I would like to write okay, so the transformation was y equal to u plus x, and then u is u plus x, no, yes, u plus x. How is this possible? No, but there is some, I've done something. So u was equal to, no, okay, so u was equal to y minus x, so the other one is b. This is u and this is b. Did I even write it correctly here? U and v, yes. Okay, so we get one more time. U equal to, okay, so y equal to this plus x, and then you get that v is equal to y plus x, which is u plus x plus x. So this means that x is equal to v minus u divided by 2, and then y is equal to e plus u divided by 2. So you get this. Now if I use the information that I wrote here, I got that v is less or equal than 1 is less or greater or equal than v minus u divided by 2. This is 1. I guess you have to play in some, I don't know, in some way with these expressions. And here you get u less or equal than v plus u divided by 2, greater or equal than v plus u divided by 2 minus 1. And this is, yeah, I don't know actually. This would give us v minus u less or equal than 2v less or equal than 2. If I sum it, I don't get anything. I don't know. You have to play. You have to play with this bounce in. You have to play with this bounce in the correct way, and then you will get. You will get. I didn't do this calculation, so I did the linear transformation analysis that I did above. But I guess that if you look at this. If you look at these things properly, you should be able to get. Let me. I will do the calculations now, and I will upload the notes, so you get another way. I mean, you get the solution to this too. So this is one possibility. One possibility is this one. So now I'm going to do the calculation properly. Okay, so I'm gonna close this meeting and I'm going to upload the notes with some more details about this change of variables. Yes. I'll see you tomorrow. Is cancelled. I've seen the schedule, so the next seminar is on Friday.
Okay.
Yeah.
Bye.
Bye bye. Bye.